So yeah, find the internal forces at C plus and D. And we're going to see that there is a difference because there's a point load acting on point C. When I say just to the right, I'm talking about infinitesimally to the right of where that 8 kip load is being applied. And if I was talking just to the left, again, infinitesimally to the left. And it does make a difference internally what the shear force is going to be if I'm just to the left of C or just to the right of C. But really, they're both C plus and C minus are both 8 feet away from point A. We're just moving a tiny bit to the right or a tiny bit to the left. Before we get to these internal forces at C and at D, I need to start by solving the external problem, because as we're going to see when we get to the internal pictures, we're going to need to know AX and AY and or the value of B, so that we only are going to have 3 unknowns in the additional pictures that we're going to draw. So first thing, I treat this just like a chapter 5 problem. I want to know what's happening at the pin at A and the pin at B. This is completely external. Okay, so I have those external loads of 8 kip and a couple of 40 kip feet. And then my reactions at B, I have this roller. At A, I have a pin connection, so I have a Y component and an X component. And it's statically determinate. There's only 3 unknowns. And I can solve this again just like I would in chapter 5. Three unknowns in my picture. If I sum forces in the X direction, I can determine that that X component of the pin is 0. If I sum my moments around point A, I'm going to have a moment from this couple. So I have 40. I have a moment from the 8 kip force that's 8 feet away, so minus 8 times 8. And a moment caused by By that's 24 feet away, and that's going to be a plus 24 By. By taking the moment around A, I'm left with just By as my unknown. So By I'm going to get is 1 kip. And finally, I can find Ay by summing forces in the Y direction. I'll have Ay plus By minus that applied load of 8. So Ay has to be 7 kip. Again, here, nothing new. This was from Unit 2, from Chapter 5. But we want to do this as the first step. So now the new part, finding the internal loads at these 2 locations. So the order I do it in doesn't matter, so I'll start with just to the right of C. So I need another internal picture drawing just to the right of point C. So I have my choice here. I have to make a cut just to the right of point C. And I can keep everything to the left of that cut or everything to the right. Again, I'm assuming, or I'm going to make the cut orthogonal to the beam here when I draw this because it doesn't say otherwise. So I'll make an orthogonal cut, everything to the left or everything to the right. Generally, I just want to keep the side that has less going on. So I decide in my notes to take everything to the left of C, but you'll get the same answer if you take everything to the right of C plus, really. So in my picture, I'm keeping everything to the left of C plus. I have in my picture the reactions at point A. I found that AX was 0. I found that AY was 7 kip up. BY was also up. So I have here at A 7 kip load from the pin reaction. Again, had I not drawn this first, I would not know that 7, and that would still be an unknown, and I wouldn't know that AX was 0, which I'm not even going to draw here. That's why the external picture is a good place to start. Also in this picture, because I'm cutting just to the right of point C, I will in this picture see that 8 kip force acting just to the left of my point. So that will be in this picture. If I were looking at C minus, or just to the left of point C, I would not see that 8 kip load. And that's the difference between just to the left of C or just to the right of C. Am I including the 8 kip load or not? So external to my picture, that's all that's happening. So what I have to now include is, because I cut it apart at point C, I have to include what was the other part of the beam doing to this part of the beam when they were bonded together. And that's what these internal loads are. I have an internal normal force I'll call P sub C. Since this is my cut surface, it's out from that, out and perpendicular to that surface. So it is pointing to the right or in the positive x direction, but that's the direction it's pointing because of the cut surface, not because it's the positive x direction. I also potentially will have a shear force I'll call V sub C. Again, referring back to the sign convention we use, because this cut surface is on the right side of my picture, I'm going to assume that VC is down, and I'm going to assume that the internal bending moment is counterclockwise. Now, had I chosen to keep the other side of my picture, I'll just draw briefly what that would have looked like. If I kept everything to the right of C plus, I would have had the force from By. I would have had that moment, that 40 kip foot moment. Because I'm cutting just to the right of point C, this picture would not have that 8 kip load in it. I would have PC now pointing to the left, and by convention, I would have assumed VC was up, and that MC was clockwise. If I do the equations out of this or this, I will get the same numbers and signs for PC, VC, and MC. But I only need to do one of them to get that. Again, we want to stick to that sign convention for beams if we have a 2D shape. But either one will get the same answer. And because again, in contrast, if I was looking just to the left of C, the 8 kip would not be in this picture, but then this picture would have the 8 kip load. And we'll see what's that going to affect? It's going to affect the value we get for VC. So I'll get rid of that for now. I just need to analyze this picture. I've introduced 3 more unknowns, but I can get 3 more equations. In the x direction, I have just PC pointing to the right. It turns out that the internal normal force is 0. We have the same interpretation, though, that we did for trusses. If our internal normal force is positive, as long as we use this convention, positive will mean tension, negative will mean compression. In this case, at point C, it's not in tension, nor is it in compression. I can analyze my forces in the y direction. So I have 7 up, I have 8 down, and then the way that I assumed my direction for VC, in my picture, it's pointing down. So according to my sign convention, I get that VC is -1 kip. And if I sum moments, the most convenient point to take the moment around is C. The internal normal force is acting through the centroid, so that will not contribute to the moment. VC is acting through the centroid, so it does not contribute to the moment. I will have MC, which in this picture I assume is positive or counterclockwise, so it's positive in equation 6. I'm cutting just to the right of C. I'm going to say that 8 kip is passing through point C, or it's so close that I would be multiplying it by such a small value, it's not going to matter. So I will say that the 8 kip acts through the centroid, so it's not in this equation. So I do have that 7 kip load, so I'll have a -7 times its distance of 8 feet away. So I get my internal bending moment is a positive 56 kip feet. Again, these values are specific to point C, and also specific to a orthogonal cut through the length of point C. I can't necessarily say that the internal normal force is 0 everywhere, even though in this case it actually is. And I can't say that the internal shear force is -1 kip everywhere along the length of the beam, which it's not. And I cannot say that the internal bending moment is 56 kip feet everywhere in the beam. I can only say that's true at point C. We will see in EMCH 213 how we can find these values everywhere along a beam more simply than doing this, but we'll get to that later. I now need another picture to see what's happening at point D, because nowhere in any of these pictures is there an internal force that's acting at point D. Another cut has to be made, and at point D, because there's no couple acting at point D, because there's no point load acting at point D, there's no difference if I look just to the left of D or just to the right of D. The only reason that was a concern at C is because I had a point load acting there. Oh, and actually, going back a step, had I analyzed just to the left of C, this picture would not have had that 8 kip load there, which means that equation 5 would not have had this 8 in it, which means that VC would have been positive 7 kip rather than -1 kip. So going from the left to the right, I have a shift of the value of my internal normal, my internal shear force, just to the left of C versus just to the right of C. So that's why there is a difference between looking on the left side or the right side. At D, though, there is no difference there. So I'm just going to call this picture D. I'm going to make a vertical slice through point D. I can keep everything to the left or everything to the right. In this case, I'll just keep everything to the right of point D and draw that. I have BY of 1 kip that I determined earlier was acting up. The applied couple of 40 kip feet. And those are the only external loads acting on this section. And then now at point D, where I've split it from the rest of the beam, I can now see the internal loads. They're acting at point D. I have the internal normal force acting through the centroid and out from the surface of the cut, which is going to be in the -x direction. But again, it's because of the side that I kept, it's pointing to the left. I now have my cut at the extreme left of my picture, which means I'll assume that V sub D is up in this picture, and I'll assume that M sub D is clockwise in this picture. Again, notice the difference. Here my cut was on the right side of my picture. Here the cut is on the left side of my picture. So my assumption about the direction of V and M has reversed. That's my full free body diagram for D. I've introduced, again, 3 more unknowns, but I have a new free body diagram. In the x direction picture D, I'll have a -P sub D. The internal normal force is also 0 at point D. It's not in tension or compression. In the y direction, I will have here, I assumed VD was up, +1. I find that at point D, my internal shear force is also -1 kip. I should point out, tension or compression for internal normal force is based on positive or negative, like we saw with trusses. Shear force does not have tension or compression. I can't say this is 1 kip in compression. I'm just going to say it's -1 kip. I don't have that interpretation. And same thing for the internal bending moment. This is not 56 in tension. I'm just saying it's positive 56. Later when we look at stresses, these will contribute to a tensile stress or a compressive stress, but the load itself is not going to be tensile or compressive. And I'll take the sum of moments around point D, the centroid of that cut surface. I'll have a -MD from the internal bending moment, since I'm assuming it's clockwise in this picture. PDX through the point, VDX through the point. I'll have a +40 from the couple. And, I forgot here, that's 8 feet. I'll have a 1 times 8, also positive, from the 1 kip load, 8 feet from point D. The only unknown here now is MD. And MD, I get a +48 kip feet.